Our next speaker, we have Mr. Gurpreet Sachdeva, Assistant Vice President Technology from Capgemini. Gurpreet is a technology executive with 24 years of experience working on some of the most challenging technologies related to communication software, DevSecOps, cloud computing, and cybersecurity. Gurpreet did his BTech CS from NIT, Kurukshetra, and MS Software Systems from BITS Pilani. He is Cloud and DevSecOps Solution Architect in Altran and leads the DevSecOps practice. Gurpreet has led DevOps transformation initiatives for multiple customers across different industries and geographies. Gurpreet is a published author and frequent speaker in the prestigious conferences. His topic for today is continuous monitoring in DevOps Pipeline.
Hello, DevOps India community, and welcome to the session on continuous monitoring in the DevOps pipeline. I'm Gurpreet Sachdeva, and I'm a cloud and DevOps architect based in Gurgaon. I work for Capgemini India. I'm a co-founder of Delhi NCR Java user group and regularly blog on Java and DevOps related topics. I've written a book on the ELK stack and also launched a video course on DevSecOps. Just in case if you want to chat with me later, these are my coordinates on Twitter and LinkedIn. In this session, I want to talk about how to continuously monitor our systems in the DevOps environment. DevOps practices advocate shift left of testing and also shift right of feedback. In fact, the three ways of DevOps. The second way is all about creating the right to left feedback loops. And the modern systems have become increasingly complex with the use of microservices, cloud native architectures, and horizontal scalability. And by the very nature, distributed systems are prone to failure. Monitoring techniques like logs, metrics, traces help in tracking any abnormal situations. I will also cover observability techniques, which help in keeping an eye for unknown situations. The DevOps movement has its origins in the seminal talk given by John Allspaw and Paul Hammond of Flickr at the O'Reilly Velocity 2009 conference. They described how they can perform 10 deployments per day, and this approach became popular as DevOps. The born in the web companies like Amazon, Facebook, Google, Netflix, and many others laid the foundation of DevOps movement. Adoption of DevOps practices leads to tremendous benefits in terms of throughput and system stability. The Accelerate State of DevOps report points out adoption of DevOps practices transforms normal teams into elite teams. These elite teams have significantly better deployments, lead time, incident recovery time, and lower change failure rate as compared to low-performing teams. The values and philosophies that frame the processes, procedures, practices of DevOps can be described by the three ways. The first way of system thinking is about the performance of the entire system, as opposed to the performance of a specific silo of work or department. The idea is to focus on the business value streams. The second way of amplify feedback loops is about creating the right to left feedback loops. And the third way of culture of continual experimentation and learning encourages to take risks and learn from failure. While the DevOps practices are generally associated with shift left testing, but it also emphasizes shift right of feedback. This is quite evident from the second way of DevOps. The second way stresses the importance of feedback from right to left in a process. In order for this to be successful, the feedback loops should be short so that information is received in a timely manner. Continuous improvement must be integral to the process, and the feedback loops need to provide information to feed the continual improvement. Feedback helps us in improving our system. This involves retrieving signals from the system and sending them back to the beginning of the system for improvement. This is what allows more generally an organization to improve. The idea is to measure the flow of work done through the system. If the duration of the cycles is measured, then the feedback will make it possible to reduce them. For example, measuring the loading time of web pages allows us to take action to make website users happier because pages load faster. Another benefit of continuous feedback is to make sure that people have the information that they need. This may include metrics from different places, like you can collect server metrics like disk space, CPU utilization, etc. You can measure the pass-fail ratio, the coverage of a unit test. You can measure certain KPIs like turnover, gross margin, etc. You can also do in your retrospectives things like postmortems, and you can also set up deadlines for setting a reasonable value for MTTR, mean time to recovery. So all these are different examples which you can use to have a continuous feedback in place. If it is useful to study what went wrong, it is also useful to see what went well. For example, if there's a significant change, say significant failure rate in running unit tests, it means that there's a development problem. Even if it is rather correct, there is a need to improve it. Once these improvements are in place, you need to continuously monitor them. We all know modern systems have become increasingly complex with the use of microservices, cloud-native architectures, and horizontally scalable architectures. Legacy systems were primarily based out of monolithic architectures, and monolithic systems, as you know, can have challenges related to scalability. However, the system maintenance and orchestration is easier as there are fewer moving parts. As started migrating to microservices-based architectures, we have a lot of smaller pieces of code running in their own sandbox. This is great from horizontal scalability perspective, but the management of entire system has become quite complex. By their very nature, distributed systems are prone to failure. There are a lot of components and they all need to be monitored properly. You can see the mesh diagram of various services being used in Amazon.com and Netflix. This will give you an idea of the magnitude of services and their interdependency. And we have some interesting statistics also. For in case of Amazon, every 100 millisecond of latency has cost them 1% in sales. Similarly, Google found an extra 0.5 seconds in search page generation drops the traffic by 20%. This implies that there are some consequences on business if system is not working optimally. Hence, the need to continuously monitor and measure different system performance parameters. Monitoring systems provide various benefits, like you can analyze long-term trends. For example, you can see how big is your storage space and what is the projection. You can compare over time or experiment groups, for example, examine different tweaks for architectural choices. You can have alerting in place so that you can check what is broken or what is about to be broken. You can build dashboards to give a bird's eye view of system performance and also conduct ad hoc retrospective analysis and debugging. Monitoring a complex application is a significant engineering endeavor, and it should address two key questions. What's broken and why? The what's broken indicates the symptom, the why indicates the cause. For example, if the response is slow, The cause could be overloaded CPU or network congestion, and good monitoring system should clearly distinguish between what and why so that there is minimal noise. Ideally, we should rely more on white box monitoring with modest use of black box monitoring. Black box monitoring is symptom oriented and represents active, not predicted problems. For example, the system isn't working correctly right now. We can use uptime checks, port status, and latency checks for black box monitoring. In situations like when we have to page someone in the middle of night, black box monitoring has the key benefit of forcing discipline to only call an engineer when the problem is both already ongoing and contributing to real symptoms. On the other hand, for not yet occurring but imminent problems, black box monitoring is not that useful. White box monitoring, on the other hand, depends on the ability to inspect the innards of your system, such as logs or HTTP endpoints with instrumentation. White box monitoring therefore allows detection of imminent problems, failures masked by retries, and so on. Tracing, logs, and metrics are the three key techniques for white box monitoring. White box monitoring is sometimes symptom oriented and sometimes cause oriented, depending on just how informative your white box is. In a multi layered system, one person's symptom is another person's cause. For example, suppose that a database's performance is slow. Slow database reads are a symptom for the database engineers, who is detecting them. However, for the front-end engineer, observing a slow website, the same slow database reads are cause. So when collecting telemetry for debugging, white box monitoring is essential. If your web server seems slow on database-heavy requests, you need to know both how fast the web server perceives the database to be and how fast the database will leave itself to be. Otherwise, you can't really distinguish an actually slow database server from a network problem between your web server and your database. Proper metrics-based monitoring is a mixture of both technical and business data. When defining metrics to be monitored, oftentimes people use the means of some quantity, kind of an average. For example, the mean latency, the mean CPU usage of your nodes, or the mean memory usage. Both CPU and memory can be utilized in a very imbalanced way, and the same holds for latency. So if you run a web service with an average latency of 100 milliseconds at 1,000 requests per second, 1% of requests might easily take more than 5 seconds. If your users depend on several such web services to render their page, the 99th percentile of one backend can easily become the median response of your frontend. A simple technique to differentiate between a slow average and a very slow tail of requests is to collect request counts bucketed by latencies rather than the actual latencies. For example, how many requests did I serve that took between 0 millisecond and 10 milliseconds, between 10 milliseconds and 20 milliseconds, and between 20 milliseconds and 50 milliseconds, and so on. This can provide easy to visualize distribution of requests. Different aspects of a system should be measured with different levels of granularity. For example, observing CPU load over the time span of a minute won't reveal even quite long-lived spikes that drive high tail latencies. On the other hand, for a web service targeting 99.9% availability, probing for a 200 success status more than once every 1 to 2 minutes is probably unnecessarily frequent. Similarly, checking hard drive fullness for a service targeting 99.9% availability more than once every 1 to 2 minutes is probably unnecessary. Also, carefully structure the granularity of your measurements. Collecting per second measurements of CPU load might yield interesting data, but such frequent measurements may be very expensive to collect, store, and analyze. The sources of potential complexity are never ending. Like all software systems, metrics dashboards can become quite complex with interrelated dashboards, and it makes it difficult to correlate the observations. Therefore, design your metrics monitoring with an eye towards simplicity. The metrics dashboards that catch real incidents most often should be simplified. Any metrics which are rarely observed should be removed as a normal hygiene process. Logging is quite invaluable as exporting information about each operation and about system makes it possible to understand exactly what a process was doing at a given point in time. You may need to analyze system logs across one or many processes. Tracing requests through the whole stack provides a very powerful way to understand how a distributed system is working. The varying use cases imply significantly different tracing designs. In the normal mode of working, no one needs to look at this information, but it is recorded for diagnostic or forensic purposes. The expectation is that no one reads logs unless something else prompts them to do so. Well-designed systems should have proper logging to track new version deployments and configuration changes at all layers of the stack, from the server binaries handling user traffic down to the packages installed on individual nodes in the cluster. Text logs are very helpful for reactive debugging in real time, while storing logs in a structured binary format can make it possible to build tools to conduct retrospective analysis with much more information. There is a plethora of monitoring tools from which we can choose from. Each of these tools address specific areas. We have Nagios, which monitors systems, networks, and infrastructure. Prometheus is used for event monitoring and alerting. Splunk captures indexes and correlates real-time data in a searchable repository from which it can generate graphs, reports, alerts, dashboards, and visualization. Sensu is an open source infrastructure and application monitoring solution that monitors servers, services, and application health and sends alerts and notifications with third-party integration. Flapjack sits atop existing monitoring engines like Nagios and Sensu, processing events and depicting failures. For log management, we have the Elastic Stack, which comprises of Elasticsearch, Logstash, and Kibana. Logstash collects data from a variety of sources, transforms it on the fly, and sends it to the desired destination. It is most often used as the data pipeline for Elasticsearch. Beats are lightweight data shippers that act as agents on your servers to send specific types of operational data to Elasticsearch. Elasticsearch provides a distributed, multi-tenant, capable full-text search engine with an HTTP web interface and schema-free JSON documents. Kibana provides data visualization dashboards using Elasticsearch APIs. FluentD is an open source data collector which lets you unify the data collection and consumption for a better use and understanding of data. It can also be used with Elasticsearch. Then we have CollectD, which is a very simple Unix daemon that collects, transfers, and stores performance data of computers and network equipment. Similarly, StatsD is a daemon for easy and powerful stats aggregation. Graphite is a free open source software tool that monitors and graphs numeric time series data, such as the performance of computer systems. And then Grafana is a multi-platform open source analysis and interactive visualization web application, which provide charts, graphs, and alerts. InfluxD is an open source time series database suitable for operations monitoring, application metrics, Internet of Things kind of sensor data, and real-time analytics. Uchaiva is again a simple dashboard for the Sensu monitoring framework. And then we have Graylog, is a leading centralized log management solution for capturing, storing, and enabling real-time analysis of terabytes of machine data. So as you can see, there are a lot of tools. They all have their own pluses and minuses and their own features. You can pick, whichever is applicable, whichever is more suitable for your requirements. The monitoring ecosystem should ideally consist of a data collector and then store it somewhere, and then use this data to visualize and send alerts based on analysis. You should design your monitoring system by taking care of different aspects. The most fundamental part of any monitoring system is the data or statistics collector. It forwards the observations or statistics to the database layer, where the data is cleaned, aggregated, normalized, and stored for further access. It may also remove false positives. The visualization layer fetches from database layer and shows monitoring data in different types of graphs and dashboards. This helps in proper understanding of the collected data. The alerting layer checks the data for any anomalies and then raises notifications or alerts. These alerts can show up on visualization dashboards or can be integrated with alerting tools, with email clients also and pagers. You can see that the different types of tools have been arranged in this slide as per the functional categories. Data can be collected by tools like Logstash, CollectD, StatsD, Prometheus, Nagios, or Sensu. The collected data can be stored in Graphite or the internal repositories of tools like Nagios or Prometheus. The time series data can be stored in InfluxDB. Grafana provides comprehensive dashboards on top of the collected data. Similarly, Kibana can be used for creating logs dashboards on top of Elasticsearch. Sensu, Nagios, or Flagjack can be used for alerting different clients in case there are any anomalies. You may notice that there are many tools which come with comprehensive capabilities and are suitable for more than one layer. And that's the beauty about it. Again, as you can see here, there's more than one tool which is applicable for a particular layer. And it's up to you, your suitability, your application, and when you can pick the appropriate tool. Since we have started using microservices, containers, cloud native architectures, DevOps, CI/CD, etc., we have new challenges for tracking the system and performing incident management. We now need a change in mindset and need to complement monitoring with observability. Monitoring focuses on known unknowns, like certain things which can go wrong. For example, we know that when the disk becomes full, the application would crash. So we can continuously monitor the disk usage and alert when the disk is near getting fully utilized. Observability, on the other hand, tries to create a system where we don't know what will go wrong and when will it go wrong. But when it does go wrong, we have enough information to perform further investigation. Also, as per the control theory, observability is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. We would like to query the system in production environment without disturbing the system state. In order to make it successful, make sure that your applications are observable and can externalize the state without any impact on functioning. While monitoring is about overall health, observability is more concerned with providing fine-grained insight into system behavior with rich context for debugging. The mindset behind observability can be better understood using the concept of survivability bias. So there's a very interesting story which has its roots in World War II. It's around the survivability bias. So during World War II, the engineers were looking at ways to improve the planes by looking at them when they used to come back. So they used to see the impacted area and thought that, okay, this is where the improvement should be done. It sounds logical. as the impacted area can immediately grab attention. It is similar to how we do monitoring. We see the impact in an area which we know, right? It's kind of like known unknown. However, a statistician by the name of Abraham Ward told the engineers that they are making a logical error. They're focusing on what they see. Instead, they should focus on what they don't see. So the idea being, you are seeing the hits on the planes which are coming back. So, but these planes were successful to come back. Just think about those planes which were hit in other areas and they were not able to make it back. So essentially, look for stuff you don't usually see. This is the principle of observability also. Look for unknown unknowns. So it is important to focus on the unknown factors impacting system performance, and hence it becomes essential to complement monitoring ecosystems with observability tools also. There are, of course, certain challenges when we start using observability. Most of the time, the data is logged up inside a vendor solution. Data is not readily available across enterprise. There are different tools for different use cases, and the ever-changing landscape of different tools, products, and services, and sheer volume of data can be overwhelming. This situation can be simplified by using a decoupled observability pipeline, which addresses the aspects related to what data to send and where to send it. The first step is to structure your data. So move away from the old way of logging data in a free flow format. No one likes doing grep or using regex for scanning log data. Structure the information as log events with different event type for different kind of scenarios. These events should also contain the context, as it can provide more help for debugging. Different types of information can be passed in the context. You have put information which is readily available like CPU or memory utilization. Also pass information specific to your applications. The log event format can still be JSON. Make sure that you don't log sensitive information like passwords or personally identifiable information. A lightweight data collector like Fluentd or Logstash can perform transformations, filter events, and write the relevant ones to the data pipeline. These agents can then run on the host VM, to enforce the log event specification. The data pipeline should be scalable, fault-tolerant data stream, which can handle the flood of observability data being generated. It also provides actually a buffer which decouples data producers from consumer. For example, tools like Splunk can get overwhelmed by the velocity and volume of the data being generated. There are various options of tools for both data collectors and pipeline. One good candidate for a data pipeline is Kafka Streams. Similarly, you can have Kinesis Streams in an AWS cloud environment. Other public cloud environments also have their own mechanisms for data pipelines. The data router consumes data from the pipeline, performs filtering, and uses APIs to write data to the appropriate backends like Splunk, Nagios, Elasticsearch, etc. It may also perform transformations and process data, but heavy-duty processing is always the responsibility of the backend system. This logic should be in time series or monitoring backend. The data routers should be stateless and use the data type to determine how to route the data. For example, logs may be sent to Splunk, metrics to New Relic, and traces to Stackdriver. This process resonates with serverless and container-based systems also. And you don't need to boil the ocean in one step. You can take a stepwise approach, take baby steps. First of all, adopt a structured log mechanism. Move the log and data collection out of the application process. This is done to avoid spending more processing time in logs than actual logic processing. Use a centralized logging system. Introduce a streaming data solution and then introduce different consumers. The idea is to move away from host-centric model of observability to service-centric model. It maps better to container-based and serverless architecture models. By following a decoupled pipeline, you can get benefits like it's easier to change tools, maps to elastic and serverless architectures, empowers the team in silos to unlock the data, enables teams to use the tools best suited for their needs, and it's easier to change, evaluate tools. And this also minimizes the impact on developers. So in summary, we can say that while the DevOps practices are generally associated with shift left of testing, but it also emphasizes shift right of feedback. This is in accordance with the second way of DevOps. Modern systems are increasingly using technologies like microservices, cloud-native architectures, horizontally scalable systems, etc. We must keep in mind that distributed systems are inherently complex and prone to failure. Complex systems need to be continuously monitored using logs, traces, and metrics. And monitoring systems should address two key questions: what's broken and why. The what's broken indicates the system, the why indicates the cause. Observability techniques complement monitoring systems by helping in discovering the unknown unknowns. You should look at your system and service requirements before deciding the monitoring and observability targets. A decoupled observability pipeline can go a long way in providing effective and scalable mechanism to keep an eye on unexpected events. I hope you found this talk valuable. If you have any questions, I'll be happy to answer them. Thank you so much.